So we continue with the same topic. We have completed halfway yesterday, that is semiconductor. So absolute zero temperature, that semiconductor will behave like a non-conductor, and at any other higher temperature it will behave like a conductor. At a higher temperature it will be conductor, and normal temperature it will be semiconductor. So that is the nature. Because of this is happening because of the difference between the gap between the valence band and the conduction band. Now for a semiconductor, the gap should be around 1 electron volt. Okay, and if the band gap is more, then it becomes a conductor. Otherwise, if there is more, it will become a non-conductor, and if there is less, it will be conductor. Sometimes what happens, this conduction band and valence band merge together. For conductor like metal, the valence band and conduction band normally merges together. So above absolute zero temperature, what is happening? Why it is becoming conducting? See, because some of the electrons from the valence band can be promoted to the conduction band. So it becomes free electron. It becomes free electron, and freely it can flow, it can move, and that's why it becomes conductor. See here the plot, the picture here, there is certain electron that is promoted from this level to this level. So it is formed certain holes here. As the electrons are promoted at the higher level, at the conduction band, so in the valence band there are certain gap formed. So that is the hole.
So here also the holes are acting like
Temporary, this is temporary one. So the hole is actually for P-type semiconductor, and that is the major carrier for a P-type semiconductor, and for N-type semiconductor, electron is the major carrier. Major and minor. Okay, major and minor. So if we take a P-type semiconductor, their hole is the major carrier and electron is the minor carrier. And for N-type semiconductor, electron is the major carrier and hole is the minor carrier. How you get the hole and free electron? If you take some pentavalent molecule like arsenic, you contaminate the germanium with arsenic or silicon with arsenic, then what happens? Tetravalent silicon or germanium will make 4 bonds with arsenic, and the fifth electron of the arsenic, because arsenic has got 5 electrons in the outermost shell, the 5th electron will be free to move because it is not bound. So accordingly, this is called N-type because extra electron is there and electron is negative, so it is called N-type. Negative type, so N-type. P-type means positive type, where we are taking some element like boron or aluminium, okay, which is 3 valency 3. So that is making a bond with silicon and germanium. So 3 are occupied, but there is a gap generated because there is a possibility of 4 bonding, but only 3 bonds are formed. So there is a gap or hole generated. Okay, so that is the reason hole is the major carrier in case of such doping. So it is called P-type semiconductor. So you are getting P-type and N-type semiconductor. So is this N-type and P-type? Let's go ahead. So here is the free electron for arsenic because 4 bonds are made with germanium. So 5th electron is free electron as it is a pentavalent one, and we are getting this N-type semiconductor because this extra electron is negative. Electron is negative, so extra electron there, that means it is becoming negative type, so N-type. So there are some salient features or points here. The current conduction in an N-type semiconductor by free electron, it will always, electron is negative, so it will move towards the positive plate, positive terminal, and the current flow through the crystal is free electron. Then you have the P-type semiconductor, another one. For example, here gallium. Gallium is a boron. Below boron you have aluminium. Then you have gallium. Below aluminium. So it is having also 3 valence electron, trivalent. Trivalent, so 3 valence electron, and germanium has 4 valence electron. That's why 3 bonds are possible, but one hole is created because it could not make any bond here. That is the hole. So this is the major carrier. So gallium is a very good one as a doping material compared to boron or aluminium, because it is much more, as if you go for a larger molecule, the flexibility is more. If you go for a larger molecule, the flexibility is more. Flexibility means if you take boron electron is very near to the nucleus, but here it is quite away from the nucleus, so making bond will not be that much rigid, and rigidity is not desirable here. If it is rigid, then the current flow may be restricted, but here the current flow will be better. So that's why this doping of arsenic is why not then above arsenic, which one is there? What is arsenic is pentavalent. So just above arsenic, what is there? Phosphorus. Okay, pentavalent, phosphorus, nitrogen, phosphorus, arsenic, antimony, bismuth. So just above arsenic, if you look at, this is phosphorus. So phosphorus, can you expect that as a dopant? No, because it is very small size, flexibility will not be there, so it will not be a good dopant. Okay, for doping the material we are using called dopant, so it is not a good dopant. So here gallium is a good dopant, and arsenic on the other hand, for N-type, arsenic is a good dopant. So this is N-type and P-type as I already discussed. So now majority and minority carrier, that also I have told you that majority carrier for N-type semiconductor is electron and minority carrier will be hole, whereas for P-type semiconductor major carrier will be hole and minor carrier will be electron. What is hole? Hole means we can consider that just opposite to electron, means lack of electron. Okay, like we say positive current, but actually current is flown made due to the flow of electron. So when you say the heat and coldness, what is coldness actually? Lack of heat. But actually, is there any coldness? There is nothing like that. Okay, so here is also something like that. Electron or lack of electron. So hole is actually lack of electron. There are supposed to be some electron, but which is not available. That's why there is a gap generated. That we are calling hole. So in case of P-type, minority carrier is electron and majority carrier is hole. Hole means gap of electron. That is acting as a positive charge. That is acting as positive charge. Just a current flow. Current flow means we are thinking. We think it is a flow of positive charge. Okay, that is current. Current means we consider is a flow of positive charge. But actually, which is flowing? Electron. There is no positive charge that is flowing. Okay, electron is flowing. Now, PN junction. You have taken some N-type germanium and some indium on the surface. So this type of, this is N-type and this indium, gallium, indium. What is the family of indium? What is the family of indium? Just below gallium, and gallium is below boron family. Exactly. So boron family, that means it is P-type, supposed to be P-type material. Now, but this is pure indium, so it is not a semiconductor here at this case. So it is used as a dopant, with small quantity used. But here this one is N-type because germanium contains N-type, but here you have added some indium on the surface, just maybe a small drop. After that, when this indium will percolate through the germanium to some extent, then this N-type and P-type both will be available at the same place. So it will be called P-N junction. So P over N, this is N, over N you have just put certain amount of P. So there is maybe a small drop. That is called P-N junction. Similarly, you can have N-P junction. Okay. So what is happening here? This material, this indium, it is actually melting point is very low. Boron as you are going the periodic table downward in the periodic table, the melting point, what happens? Melting point decreases or increases? As you go in the periodic table downward, the melting point will. Okay. So here, this indium, it will form with a little bit of heat from the surrounding maybe. It will form a liquid or semi-solid type of state. Liquid or semi-solid type of phase. So it will form a small puddle on molten germanium indium mixture. Germanium and indium will mix together, so it is making a contamination. We are contaminating purposefully so that it will form the semiconductor, better semiconductor. So a little bit of contamination here. This indium is mixing with the germanium here, so it is germanium indium mixture at this junction. So this is called PN junction. Now, if we cool the material overall, then this will become solidified. The liquid metal here becomes solidified, and why you are making it liquid first? Because it will melt and flow, mix with germanium. For this mixing purpose, we are melting the indium here so that it can mix and flow into the germanium to some extent. After that, we are cooling the overall thing so that there is a junction generated. We are making it junction for good contact. If you just keep one thing upon another, there will be no contact. So if it flows one matter into another, there will be good contact. That we are making. First, you allow it to melt and flow, and after that, we solidify that. We are cooling that so that it solidifies and making a junction.
Sir, we have to produce the heat externally.
Little bit of heat will do. Yeah, little bit of heat. So this we are calling indium button. Just like a button. On the surface, we just giving single drop, a small piece maybe. Then it melts and flows with a little bit of heat. And after that, we again freeze the material. So it is getting fixed up with the solid, because it first is molten and then it is becoming solidified. So it will fixed on the surface like a button. So we call it indium button, frozen on the outer surface. So it serves as a soldering on lead.
Hi there. This is the first in a series of 3 videos on semiconductors. In this first video, I'll give a simple explanation of semiconductor band theory. We look at intrinsic semiconductors, then move on to doping, in order to form N-type and P-type semiconducting materials. So, first of all, we're going to look at the element silicon, although other semiconducting materials are available. Silicon has the symbol Si and an atomic number of 14. This means that silicon atoms contain 14 electrons. 2 in the first shell, 8 in the next, then 4 in the outer shell. We refer to these outer electrons as valence electrons. These are the electrons which can form chemical bonds. Now we'll simplify a model of the silicon atom to show only the 4 outer valence electrons which take part in bonding. In individual atoms, the electrons can only occupy discrete energy levels. The production of line emission spectra and line absorption spectra can be explained in terms of the electrons moving to different energy levels and either emitting or absorbing a photon, although that's covered in another lesson. When a large number of atoms come together to form a solid, the energy levels become reorganized into bands as the atoms interact. Each energy band actually consists of many closely spaced energy levels. You can see from the diagram on the left that all 4 of the silicon atoms' outer electrons form covalent bonds with the neighbouring atoms. Now, out of interest, the diagram on the left shows what's known as the semiconductor bonding model. At 0 Kelvin, all of the outer electrons are bonded. The diagram on the right shows the energy band model. In order to explain the electrical properties of semiconductors, we only need to consider 2 energy bands, the valence band and the conduction band. These are separated by a band gap, which we'll discuss later. What I've not mentioned yet is that this is an undoped semiconductor of pure silicon, what we call an intrinsic semiconductor. As I said before, at 0 Kelvin, all the outer electrons are bonded. Let's look at what happens when we add some heat. an electron has gained enough energy to break the covalent bond and is now free to take part in conduction, meaning that the resistance of the material is reduced.
What we are learning here is intrinsic semiconductors, pure one, without any doping. So like silicon, germanium, this type of material, if little bit of heat applied, it can current can flow because the conduction band and valence band gap is small. So you are supplying heat, so the electron is actually displaced from here to here. Somewhere in the interstitial space, the electron is displaced, and that's why this electron is becoming a free electron, and then it can flow.
The absence of the negatively charged electron in this position leaves behind a net positive charge, which we call a hole. In terms of energy bands, the electron, which was initially in the valence band, jumps to the conduction band, leaving behind a hole in the valence band. The band gap, or energy gap, is just the energy required for the electron to break the covalent bond and jump into the conduction band. As the semiconductor is further heated, more covalent bonds are broken, resulting in more electrons jumping to the conduction band, with more positive holes created in the valence band. So as the temperature of a semiconductor increases, its resistance decreases due to the motion of the electrons in the conduction band and holes in the valence band. If we look at the diagram on the left, we can see that electrons from neighbouring atoms can move to fill a hole, leaving behind a hole in their previous position. Although strictly this was caused by the motion of negative electrons from left to right, we can also describe.
Could you follow that how the electron is moving? Actually, we just think that how the hole can contribute in the electron flow of electricity, right? So here you just look at here. So first of all, the hole was created here. Then it is this hole is changing. Hole is moving as a whole. Okay. So the hole is moving. So initially the hole was here. Now the hole is here. That is the way it moves.
As the motion of positive holes from right to left. Next, we'll look at energy bands in a little more detail. As I said before, we only need to consider the valence band and the conduction band in order to explain the electrical properties of semiconductors, and for that matter, conductors and insulators. Remember then that in order for a material to conduct, it must have electrons which are free to move within its conduction band or holes in its valence band. In a conductor, conduction can actually be
for a conductor, conducting material, valence band and conduction band actually merge together. That's why there is only one band. So there is no gap at all, and continuously electron can freely move. That's why all the metals are conducting, and they are suppose sodium, large number of sodium atom is connected together forming a molecular orbital, suppose MO. So if you know already that if there are two atomic orbitals involved, how many MO we get? 2. So n number of atomic orbitals from one side and n number of atomic orbitals from the other side, if they combine together, how many number of molecular orbitals we get? 2n number. So that if now the n is large, suppose the n is large, then 2n will be very large. So that very large number of levels will be just packed together into certain region. That is the band here. So that is called metallic band. Band theory. Okay, what is band? MO. You can start with MO. Get the idea. Certain number of atomic orbitals if combined, the same number of molecular orbitals will be generated. So n plus n, 2n number of molecular will be generated for a piece of metal. So large number of energy levels packed together, making a band. It is called band. Now we have the valence band and conduction band. For conductor like metal, these two bands are merged together, and it will be partially filled because we have sigma and sigma star type of all levels merged together. So that's so many sigma and so many sigma stars will be merged together, and obviously all will not be filled up because stars are usually unfilled. So half will be filled, so it is called partially filled. Conduction band is partially filled. Now here the gap is large, that's why electron cannot jump from here to here. It cannot. So that's why it is insulator. And when the gap is small, then electron can move from this valence band to conduction band, and it is called semiconductor. That is the difference, nothing else.
Explained by considering only the conduction band. The conduction band is only partially filled, so electrical conduction is permitted. Unlike a semiconductor though, increasing the temperature of a metal conductor will actually cause its resistance to increase. This is because the number of electrons within the conduction band increases so much that they have less freedom of movement. Remember that in a conductor, the highest occupied energy band, the conduction band, is not completely full. In insulators, there's a very large band gap between the top of the valence band and the bottom of the conduction band. At 0 Kelvin, the valence band is completely full and the conduction band is completely empty. At higher temperatures, electrons don't normally gain enough energy to jump from the valence band to the conduction band. So with no electrons in the conduction band, conduction isn't possible. For an insulator then, the highest occupied energy band, the valence band, is full. Finally, semiconductors have a very narrow band gap between the valence band and the conduction band. Like insulators, at 0 Kelvin the valence band is completely full and the conduction band is completely empty. But since the band gap is so small, as temperature rises, some electrons can gain enough energy to jump from the valence band to the conduction band, leaving behind holes in the valence band. As temperature increases then, the resistance of the semiconductor is reduced. Next on the agenda is doping. Here on the left, we see the bonding model of an intrinsic semiconductor, silicon.
Extrinsic.
With the addition of impurity atoms during the manufacture of the semiconductor, we can reduce its resistance. This is done in one of two ways. By doping with a group 5 impurity atom, such as arsenic as shown here, we end up with an extra electron. The energy level of this fifth electron is within the band gap, just below the conduction band. The energy levels associated with the extra electrons are known as donor levels. Even at room temperature, most of these electrons will gain enough energy to jump into the conduction band, thus reducing the resistance of the semiconductor. We call this an N-type semiconductor since the majority of conduction is due to the negative electrons within the conduction band. Remember that we previously discussed the heating of an intrinsic semiconductor. For each electron which jumped from the valence band to the conduction band, there was one hole left behind in the valence band. This meant that in an intrinsic semiconductor, electrons and holes exist in equal number. When we dope the semiconductor, however, this is no longer the case. In an N-type semiconductor, the majority charge carriers are electrons, and holes, which are still present due to the process described earlier, will be very much in the minority. Despite the majority charge carriers being negative electrons, an N-type semiconductor is still electrically neutral, since the impurity atom, arsenic in this case, will have an equal number of electrons and protons. Now let's look at the P-type semiconductors. This time the impurity atom, or dopant, is from group 3, so only 3 outer electrons are available for bonding with the surrounding silicon atoms. This results in a positive hole, as shown. The impurity atom in the diagram, in case you were wondering, is indium, above the valence band. These are known as acceptor levels. Electrons in the valence band require very little energy to move to the acceptor levels, leaving behind holes in the valence band. This is where P-type semiconductors get their name, because the majority charge
Acceptor level, could you understand what is happening? When we give that doping, without doping, it was having only 2 levels, one is valence band, another is conduction band. But when you give some doping, dopant is used, like here it is indium that we are using with silicon. So then what is happening? Another level is created which was not there earlier, that is called acceptor level. And some of the electrons that is promoted from valence band to this acceptor level. Why it is happening? Because you are giving some impurity. So due to that impurity, another level is created. In the pure state, there will be only conduction band and valence band. But whenever you are using some dopant, some additional impurity, so additional some energy level is also created, because the it is just like acting a catalyst. If you add catalyst, what happens? Your activation energy goes down. Actually, activation energy goes down and reaction goes in a different pathway altogether. That's why activation energy goes down. So here also, to make the thing simple or easier, to make it easier, we are using some dopant. So what will happen? Another energy level is created, that is called acceptor level. And here some of the electrons from the valence band is promoted to this acceptor level. So the gap is this band gap is decreasing. That is the purpose. We are giving the doping.
carriers are positive holes. Conduction in a p-type semiconductor is due to the motion of these positive holes within the valence band. Again, p-type semiconductors are electrically neutral, since the impurity atoms have an equal number of electrons and protons. So, that's us for now. In the next lesson, I'll be discussing the formation of a p-n junction and how it performs when forward or reverse biased. The third lesson will cover applications such as the LED and solar cell. Make sure to watch them too. For more information on upcoming videos, summary sheets and so on, visit physics-podcast.co.uk. Thank you for listening.
I have marked the second lesson also.
This is the second in the series of 3 videos in semiconductors. I'll be discussing the formation of a p-n junction and how it performs when forward or reverse biased. Applications such as the solar cell and light-emitting diode will be covered in the next lesson. Let's get started then. The diagram on the left shows a semiconductor crystal which is doped so that one side, the left-hand side, is p-type and the other, the right-hand side, is n-type. Remember from the first video that the majority charge carriers in a p-type semiconductor are positive holes, and in an n-type semiconductor, the majority charge carriers are negative electrons. Despite this, both are electrically neutral. Where the p-type and n-type regions meet is known as a p-n junction. Here, electrons from the n-type material move across the junction and combine with holes from the p-type, and vice versa. This is a process known as diffusion, which creates a region within the semiconductor known as the depletion layer. The depletion layer is effectively an insulator due to the lack of majority charge carriers within it. The p-type region within the depletion layer now has a net negative charge due to the electrons diffusing into it from the n-type material. Similarly, the n-type region has a net positive charge due to the holes diffusing into it from the p-type.
What is the major function of semiconductor? Control current flow. Control current flow. If you want current flow, you can give conductor. But we want control. Whenever required, we will allow the current to flow. And if not required, you can stop. So just like a switch, make it on and off. So that way semiconductor can be controlled. The current flow is controlled. That is the way. And more or less, but millions of regulator if you want, then it is practically not feasible. So with semiconductor you can do that. Suppose you have a lot of regulator together at the same very small plate. Hundreds of regulators in a small plate. Not possible, no. So there you can use semiconductor. So current will flow or not depends on a little bit of manipulation. That will do.
Material. Because of this, a potential difference is set up between the ends of the depletion layer, known as the junction voltage or potential barrier, which opposes the flow of further charges across the junction. In order for the p-n junction to conduct, this junction voltage must be overcome. Now let's turn our attention to the diagram on the right. Here we can see the energy band model of a p-type semiconductor, where conduction is due to the motion of positive holes within the valence band, and n-type semiconductor, where conduction is due to the motion of negative electrons within the conduction band. When a p-n junction is formed, the energy bands warp like so. The region in the middle is the depletion layer. Fully explaining the energy band model of a p-n junction goes well beyond higher physics, so I'll not attempt it here. You can see though that the conduction band in the n-type has been lowered, and the valence band in the p-type has been raised. This is the electrical symbol for a p-n junction diode. We'll learn how it can be made to conduct when forward biased, but before that I should explain that this side, known as the cathode, is the n-type side, and this side, the anode, is the p-type side. Let's forward bias it. To do that, we can connect the negative terminal of a battery to the n-type side, and the positive terminal to the p-type side. This has the effect of narrowing the depletion layer, and if the forward bias voltage is greater than the junction voltage, then the p-n junction will conduct. When looking at the energy band model on the right, you've possibly noticed that when compared with the unbiased p-n junction, the slope in the depletion layer is reduced. This makes it easier for electrons to flow from n-type to p-type across the barrier, and similarly for holes to flow from p-type to n-type. So, when forward biased, Electrons within the conduction band of the N-type semiconductor move toward the conduction band of the P-type. Holes within the valence band of the P-type also move towards the valence band of the N-type. Within the junction, electrons drop from the conduction band to the valence band and recombine with holes. Energy is released during these recombinations, and in a p-n junction diode, this is in the form of heat, which results in a rise in temperature. To reverse bias the p-n junction, we connect the negative terminal of a battery to the p-type side and the positive terminal to the n-type side. This has the effect of widening the depletion layer, and when looking at the energy band model on the right, the slope in the depletion layer is far steeper. When the p-n junction is reverse biased like this, the depletion layer has become a greater barrier to the movement of electrons from n-type to p-type and holes from p-type.
Two situations can arise. One is called biased, another is called reverse biased. So if P is connected to positive and N is connected to these two, then negative, then it is called biased. And if it is connected reverse way, that is called reverse biased. So accordingly, actually, I told you that current flow we can control. So for that purpose only it is done. Now, whenever this N-type and P-type are mixed together, then we get this depletion layer, and this acceptor level is generated. Okay, and the current flow is regulated or controlled.
To N-type.
And what is the importance of semiconductor into computer science? All the computers are made with semiconductor. Without semiconductor, computer chip is not possible, right? So that is the importance of material science into computer science. Specific material required. Otherwise, you cannot make any microprocessor, any chip. That is the main application.
There's no conduction apart from a very small current known as the reverse leakage current due to the motion of minority charge carriers. The p-n junction diode then displays asymmetric conductance. Don't worry, this is...
I think this much is enough for this part. We don't have to go much detail. The portion required we have already covered them.